Alright guys, we're going to talk a little bit about gas cycles today. Specifically, we're interested in what are they and why do we care. So to do gas cycles, we need to first look at pressure volume diagrams. I have another video on pressure volume diagrams already up. I'm not sure which order I'll post these in the end, but they're probably best watched together. So if I draw a graph with pressure and volume on different axes, y and x, then I care about cycles that we can make in this. So we would start at a given pressure and a given volume. So let's just say the exact scaling of the y-axis is important. Often they draw these with a broken axis, but just because it's convenient that way, otherwise it ends up being crammed in one corner. But if I did something like 150,000, so I'm going to do 150 times 10 to the 3, and then 100,000 here, times 10 to the 3. So a real basic cycle in terms of just what you can see on here, and this will be, we'll make this broken too. This will be, we'll make this in units of 10 to the negative 3. I should have done that with the other, but oh well, meters cubed. And this will be in units of pascals. So a real basic one would just be a square. And I talked in the other video about the different processes. So you do something like start here, go to here, this way, and this way. And so what's going to happen is during this phase, from A to B, you're going to do work. The gas is doing work, or the negative work is being done on the gas, because that's the way our formula keeps track of it, in terms of work being done. And we know work is being done because there's area under the curve. And this one, work is being done on the gas, right? So we have a positive W in this case, because there's area under this curve. Now there's no work being done in this section or that section because I can't find the area below this vertical line. I guess let me take a minute. I meant to do this at the start more so. But why do we care about these cycles? Well, these are like engines, basically. Like anything that is something we run off an engine, like so things that run off gas cycles that we can use them to understand. Are going to be car engines, refrigerators, air conditioners. I mean, anything that you can think of like that. Those are probably some of the most classic examples. Because those are ones you encounter every day in your life. But anything that is you're putting fuel into and burning it, so any type of engine that you want, boat engine, with a lawnmower, anything like that will work. There's a lot of different ways you can use this in things like that. Anything with a piston, I guess, is going to work on work off this principle. And then refrigerators and air conditioners are basically the same thing, actually. So yeah, let's talk a little bit about those. So here, because you are doing work, you have energy in the form of work leaving, right? Oh, I didn't put numbers down here. Let's say this is 2 and 3. So what we can do is we can figure out the temperature at each of those 4 points. We can just use the ideal gas law for that. I meant to draw work was leaving here. Work's leaving the gas. Work is entering the gas. and no work is entering or leaving on the sides. And so to find the temperature, we have to assume that there is no gas entering or leaving. So we're going to assume closed system. And that means that N, the number of moles, is constant. Okay. Let me calculate the temperatures and I'll be right back. So okay, I went ahead and found the temperatures. Now I assumed that I decided there was 0.1 moles of gas in here just so I'd have reasonable values for temperatures. And one thing that's interesting to me is that you can't really just look at this and tell which is the higher temperature, because if I wanted to know what temperature followed on this curve, what trend, I could say that as a function of temperature, or as a function of volume, right? We're going to solve for T as a function of volume. So I have PV equals nRT. And what my temperature curve looks like. So my temperature curve is going to look like nR over PV, right? So as my volume changes, my temperature curve kind of looks like 1 over x. So it just kind of happens that these two fall on that line just based on the way I pick the numbers. So they don't have to. It's not like there's a straight line going this way. It's actually more of a curve. Yeah. So I can definitely use other cycles besides these straight line cycles. I'll do that in a second, but I just wanted to point out, so now that I know the temperatures at every point, because this pressure and volume really gives you everything you need, I can actually start to do things like figure out how much work goes in, how much work comes out. I can figure out the change in heat, right? So I also know that we're going to have some heat flow in this one too. Let's do heat in red. We're going to have heat flowing in here because we know that because the pressure is going up, which means the particles are moving faster since my volume is fixed. I know that since the pressure is going down, I know that means my particles are going slower and hitting the walls not quite as hard. So I know that heat's leaving here. There's also some heat exchange in these two, but it's a little more complicated to figure it out. So I'm going to come back to an easy way to figure that out in a little bit, because I want to talk about the other cycles that we have. So I mentioned earlier that you could do it if you had set temperature constant. So what if I did another one of these with constant temperature? So I'm going to draw a new graph, and I'll pause it real quick. So I've started to draw my graph here, and I've got pressure on my y-axis still, which I kind of got off the side a little bit. And so one thing I'd like to point out that I did this time and before, but it's more explicit this time, is I made this one in units of 10 to the 3, even though it might look more convenient to do 10 to the 5 here, and this one 10 to the negative 3. And that way when I take pressure times volume, I can just do 100 times 2, or 150 times 3 or whatever, and not have to worry about these 10 to the whatevers, because 10 to the 3 times 10 to the negative 3 is just going to cancel itself out. So now this is, I'd also like to point out that I've changed the scaling here, because it fits better on this way. So I'm actually not breaking this axis here, but am breaking this one. So I'm going to denote that. So on this axis, I wanted this to be what's known as an isothermal curve, which means that the temperature is not changing. And that's what I said is going to look like 1 over x. So that means constant temperature. So, if I continue this pattern here, I can go like this. And then I want to do another isothermal curve to connect it. I did this math ahead, actually. This one's going to come look like that. This is also another 1 over x style curve. And then this one's going to connect like that. So let's talk about internal energy change during an isothermal curve, because we know that work is leaving the gas during this section, right? Because it's expanding, pressure's going down, but there's area under this curve, and we're going to the right, so that means work is leaving. So I can do it and still say work comes out. And I know in this case that energy is coming in through work. So when I say work comes out, I really mean energy is coming out in the form of work. I know here going in that we don't have any work we're doing, so there's no energy exchange that way. So, and I know it's gaining energy because those particles are moving faster because they're hitting the wall harder, which means that I know that energy is coming in the form of heat. And in this case, I know it's leaving in the form of heat. So what about in this case? Well, I know that for an isothermal curve, I guess maybe I'll have to post this later in the series just because now I'm talking about things I covered earlier. But I wanted to post this earlier in the series. Oh well, I'll just post it later. For an isothermal curve, the internal energy of a system, I know it's going to depend on. Nope, not the change. It's going to be some constant. We'll say monatomic, so we'll say 3/2. nRT for monatomic. So diatomic would be 5/2, but the point is it depends linearly on the temperature. So I know that for an isothermal curve, we actually have a constant internal energy. Write that down. One thing that's odd about making videos, guys, is that I feel weirder about being quiet than I would if we were actually in the classroom talking and having a normal class. All right, so what does that tell me? So for an isotherm, I know delta U is equal to Q plus W. This is work being done on the gas. This is heat coming into the gas. So I know that this is 0, and I know that the work is leaving the gas, which means that this is some negative number, which means, because work is leaving, right? Or energy leaves by work. So that means since my internal energy is not changing, I have to have an equal amount of energy come in here in the form of heat. Right? So going back up to when we were looking at earlier, it's going to be a long video. I must have energy heat entering, right? And it should be the same size, or should be, I think, more. So heat's being done like that. And down here, these should be identical. And down here, the opposite's true, right? Like, so if work is energy coming into the gas by work, energy must be leaving the gas by heat. Okay. So continuing on, there's another type of curve I want to look at, which is a curve for constant heat. And that is an adiabatic curve. And that is going to be kind of look like an isothermal curve a lot, but it's going to be steeper. And I'm going to talk more in general about these because I don't think we need to know anything about the numbers for them. Because they're a little more involved on the math side. But, I mean, you guys could do the math. I just don't think we need to. So if I take the same idea here, pressure I'm going to leave the numbers off the axes. Oh, I got on 2 papers. Whatever, we'll make it work. Actually, let's just go. Yeah, awesome. And the reason I'm doing that is because, like I said, the numbers are a little more involved, and it would take a lot of time to check it. So I'm just going to look for shapes more so. So if you have, actually, this video is long. Let's go ahead and stop this one, and I'll talk about adiabatic curves and the Carnot cycle in the next video.